we will go to our next esteemed speaker, which is Sualeh Fatehi. So really welcome Sualeh Fatehi on this talk. Sualeh is an experienced software engineer and development manager. He is an open source enthusiast and run his own project, SchemaCrawler, which is a Java library to work with database metadata. He also contributes enhancements to other open source projects. Sualeh would be speaking on mutation testing. So if you want to know more about him, you can go to this below link. And then Sualeh, you can take over from this from here.
Sure. Hello. Welcome, everybody. So I'm going to go in and share my screen. And I want to make this an interactive and slide-free presentation. So let's talk about testing in general and mutation testing and what mutation testing brings to the table, right? As developers, as testers, as software engineers in test, we're all familiar with this concept of testing our software and understanding how what we have built works and making sure that it continues to work, right? That is the whole purpose of testing. So we've come up with these concepts such as unit testing, functional testing, and so on, which help us kind of validate that our code is doing what we had set out for it to do. Right? So unit testing is great, functional testing is great, and then we say, wait, if we just do the unit testing once or the functional testing once, it's not really going to be effective, because what we really want to do is we want to make sure that our code continues to work in the future, meaning something in the environment could change, or the code itself could change as time goes on, right? People make changes, there are new requirements, and you want to make sure that the functionality is not affected. The functionality that you wanted to preserve is not affected, right? So that's the reason you write these tests. But because the code keeps evolving, you want to do regression testing. You want to repeat these tests over to make sure that over time your code continues to work. Typically that is done with every code check-in. Every time you check in code, you want to run through all your tests. So essentially what your tests are doing is that your tests are providing you the confidence that the software will work. And they're even providing you the confidence that your software will continue to work even though there are any future code changes. So you're kind of almost future-proofing your code if you have regression tests in place. But at this point, you should stop and think and say, is that enough? Because if your tests are not good enough, then what's going to happen to your code, right? So the key here is you want to make sure that you write the best possible set of tests so that you can make this assertion that my code will continue to work in the future. Okay. So some of the things that we typically do here are we sit down as a team, we discuss, we understand the functionality, we write our code, and we create test plans with the team. But people have found a way to automate this. Right? There's this concept of code coverage. So you can use a code coverage tool such as Jacoco or something else, and it will, while it's running the tests, it will take stock of what lines of code are being covered and will tell you what lines of code are being covered. Or exercised by the tests or validated by the tests, right? And it gives you this information as a percentage and as a nice chart or a graph. And then you can go and say that, okay, these areas of my code are not covered. There's a problem here. And many companies, they insist on 100% test coverage. And you say, okay, I've covered my tests 100%. It's got to be good, right? Well, as I'll show you today, maybe not. maybe even 100% test coverage is not good enough, right? And here is where mutation testing comes in. Mutation testing is a technique that you can use to measure the quality of your software tests itself. You know, the older technique, or the technique that people use most commonly, is 100% test coverage. But in addition to that, you can use mutation testing to measure the quality of your tests. And the idea for this is not a new idea. It was proposed in 1971. So you may ask, why was it not used in the last 50 years? It's an idea that's 50 years old. Why is it not used? Because it is it is very compute heavy to do mutation testing. You need a lot of computing power, and that computing power was just not available over the last 50 years. And only recently we are seeing that this kind of raw computing power has become available, right? And that's the reason there's a new interest in mutation testing, and people are starting to study what it means and how it can help them. So mutation testing is based on the following hypotheses. The ideas that mutation testing is based on is the competent programmer hypothesis, which means that the programmers who are working on the software system, they're completely capable, good people doing the best thing, and they're very good at their work. So if there is a software fault, it is probably due to a small syntactic error, maybe a copy and paste error, maybe a simple stupid mistake when you're doing a for loop or something like that. So really, you want to catch these very simple, silly mistakes that a competent programmer has made by, just oversight or being busy or something. And the other hypothesis is known as the coupling effect. Is that if you have a huge problem in your system, it is often not due to people being stupid and not understanding the architecture, or just being incompetent at a large scale in a large team. That is usually not what happens. Usually, major system faults are due to a coupling effect, where very small problems add up and then become a bigger problem in a system. So really what mutation testing tries to do is, let's go and try to find those small, silly mistakes so that they don't add up and become a huge problem. Okay? So let's understand a little bit about how mutation testing works. There's an interesting term over here, is the concept of a mutant. And what a mutation testing framework will do is it will introduce a small random change called a mutant. And this small random change is something similar to what a programmer would do by mistake, like a duplicated line of code or something like that. And it introduces this mutant or bug or change or whatever you want to call it. Let's call it a mutant. And it runs all of your unit tests again, because remember, what mutation testing is trying to do is trying to improve the quality of your tests themselves. So it introduces a small bug, runs through all your unit tests, and makes sure that at least one test fails. And if at least one test fails, then the mutant is killed. But if no tests fail, then the mutant lives. And that's a bad thing. You don't want mutants to take over the world, right? So the mutant lives. And then the mutation testing framework will repeat this again and again. So it will take that small change, reverse it, and then introduce another small change somewhere else, run through the test, introduce a small change somewhere else, run through the test. But at the same time, every time it finishes running the test, it will revert that change back to the original. So at any given time, you have only one small change in play, which is being tested for mutants. One small mutant available, and then the tests will try to kill the mutant. So it's like a game, right? And just to give an idea of what some of these mutants look like, you can think of having value mutations, where if you have constants in your code, the constant values might get changed. Or decision mutants are, if you have a Boolean or arithmetic operation, it can change that operation. For example, if you have A plus B, the mutation testing framework will make it A minus B. Or if you have something equal to something, it'll say something not equal to something, and it'll then sit back and watch what happens with that change. You can have statement mutations where an entire line of code is just randomly deleted, especially valuable for functions that return void, that don't really return anything. What would happen if you remove a random line of code from there? Or if you duplicate it, because these are the common kinds of programming errors that you see. So I want to show you how this works using a very simple example. Let's take the example of a palindrome. A palindrome is a word that reads the same backwards and forwards. For example, the word noon, N-O-O-N, noon, whether you read it forwards or backwards, it's still the same word, right? And you want to find out, you want to write a function in Java that will test whether your word is a palindrome or not, and it'll just say yes or no. And I will build this up using TDD, or test-driven development, right? And for the simplicity, just for the purpose of this talk, I want to do it in such a way that I don't want to go crazy worrying about Unicode characters and numbers and punctuation marks. I just want to say, if it reads the same backwards and forwards, we are good. Don't worry about spaces and things, right now, for the simplicity of this code. So what's the first thing you do is you write an outline of this code and you start writing some tests, right? And in fact, you want to start writing tests first. So let's start doing that. Let me start writing the tests, right? So I have already written them, and you can see them here. So I've sat and written tests for an edge case. What if you pass in a null value? Well, for the purpose of this code, we are going to say that if a null value is passed in, return true, okay, just to make it simple. So null is considered to be a palindrome, and we are just making sure that that is the case. We want to make sure that we have, if there's an empty string, we treat it as a palindrome. We want to make sure that we've tested the boundary condition of a single letter. The letter A is a palindrome because it reads the same backwards and forwards. What if you have a palindrome with an even number of words? You want to test that too, right? What about odd number of words? Odd number of letters, right? If you have a palindrome with an odd number of letters, you want to have a palindrome that returns true, like race car. Race car is a word that is a palindrome, but it has an odd number of letters. And finally, you have a negative case, right? Burning. So with this, you will say that I think I've covered pretty much all the cases, including boundary cases, positive and negative cases of what could go wrong in my function. Remember, I'm keeping it very simple. I'm not talking about Unicode. I'm not talking about checking for punctuation and spaces. Let's just keep it simple for now. So I think this should pretty much cover everything. And this is typically what developers write for a function such as this, right? So let's see what would happen if I ran the tests. And I'm going to run this, but I'm going to ask you by voice, turn on your audio and tell me if you think this all these tests will pass. You think this? What do you think will happen here?
I think all will pass. Yeah.
You think all will pass? Anybody else? Okay, let's try it out. Demos, right? I'm going to go outside. Just give me a second. Yeah, I'm going to share my whole desktop because I've got it working outside. 1 second. Okay. So unfortunately, it did not pass. right? You know why? Because you've not written any code. So this is test-driven development, is first you write all your tests, and then when you run it, nothing passes because you've not written any code. So let's go ahead and write the code, right? So here I've written some code, right? And I'll walk you through the code so that you can see what the code looks like. First thing is we want to take care of the common cases. We want to take care of null. So if the word is null, you want to assume that it's a palindrome. For the purposes of this, let's just say it's true, right? And then you want to take into account an empty string and a string that consists of a single letter or single character, right? In other words, the length of the word should be less than 2. It could either be 0 or it could be 1. If it's 0, it's an empty string. If it's 1, it's a single letter. Either case, you want to return true. So here's what we say is we say word's length should be less than 2. Yeah, everyone agree with that, right? Then, now that we know that the word is more than one letter, we can safely take the first letter or the first character, and we can safely take the last character, and then we find the center of the word, and we say, is the first character the same as the last character? And if the middle is also a palindrome, this is recursion, we are calling the function recursively. If the first character is the same as the last character, and if the center of the word is a palindrome, then the whole thing is a palindrome, right? So now at least I think the test should work. Let me give it one more try within here so that I don't have to keep shifting. No, it's still not working. I don't know why. So I'm going to try it from outside. Yeah, and you see a successful build. Excellent, right? Good, everybody? So we have got successful tests, and we think we've got pretty good test coverage. Let me show you the tests again. We've covered negative tests. We've got positive test cases, negative test cases. Let me ask you the question while I'm bringing up the coverage report. Do you think we have 100% test coverage? Anybody in the audience, by voice, turn on your volume and say, do you think we have 100% test coverage?
Yeah, it looks like.
You believe so, right? Anybody else who disagrees?
I think we all are in sync.
Yeah, everybody is in sync that it's 100% test coverage. Let's take a look. Let's take a look at the report. So this is the Jacoco test coverage report, and I'm going to show you what it looks like. It looks like this, and we've got 87% test coverage. Isn't that interesting? We thought we'd covered everything as a team, but we've not. So let's try to find out what we've not covered, right? So if you look at this function, can you see this picture here? Can you see the pop-up over here? The pop-up says 1 out of 4 branches missed, right? Was everyone able to see that pop-up?
Yeah.
So let's try to understand what this means, because this is showing us that we don't have 100% test coverage. What it's saying is that if you really study this expression, it's got something and something else. And it's saying there should be 4 ways of testing this: true and true, false and false, false and true and false. And out of those 4 ways, we have missed 1 way because it says 1 out of 4 branches was missed. So looking at the code, I'm looking at this code and I think I know which branch we have missed. We have tested true and true because we've got a full true out of this function. We've tested for false and false because we have a negative test case. And we have tested false and true. We've not tested true and true so true and false we have tested. We have not tested true and true, which is going to return in an overall false. So what I mean by this is we have tested where first character is the same as the last character and is palindrome is true, where the overall result is true, but we've not tested where first character and is equal to last character, and the is palindrome call, the first call in the recursive series, is also true, but the overall result is false. What this means is that we need to find another word which is one second, sorry about that. We need to find another word which only the first two letters are the same, but everything in the middle is not the same, right? Let's try to find that. So I am going to write one more test, and I'll show you what that test looks like. Okay. So you want to find a word that is almost a palindrome. Look at the word streets, right? Streets, S and S match, but T and T also match. And then after that, REE just doesn't match, right? So what this is telling us is that we need to test one more condition. Is we want to test where S is the same, which will give us true over here. And is palindrome, the first call is true because T and T also matches, but the subsequent calls are false. And I think with this additional test of streets, I think we will be good. So let's try it out. Let's see what happens. Okay. And now you can see that we've got the more palindrome test running. Let's see what the result looks like. And I'm going to refresh this and we are good. So we have got 100% test coverage going, which is great, right? So is this enough, really? Now that we've got 100% test coverage, is this enough? And that's the question. I'm going to run the mutation test and show you what goes on. So let's run mutation testing. And I'll show you the report. Okay. And let's look at the mutation testing report. I'm using a tool called PIT. And PIT is a well-known Java mutation testing tool. Let's see what it looks like. So even though PIT is saying, even though you have 100% test coverage, you have only 89% mutation test coverage. So you can, I'll just show you what the results look like. It has gone through all of these mutation tests, right? It has changed booleans. It has changed conditional boundaries. It has tested boolean returns. It has done all kinds of things. And at the end of it, it said, I found 9 ways to mutate your code, out of which 8 mutations were killed, but 1 mutation still lives. So let's find out what that mutation is. Which one is it? Over here on line 11, where we say word is null and word length is less than 2, this piece of code is not properly covered. Why? Let's go and look. It says, well, what the system is telling us is that it negated 2 of the conditionals and killed it, but when it changed the conditional boundary, the mutation survived. What does this really mean? So let's go up and look at the code again. So conditional boundary, this is the conditional boundary, equal to, it said I changed the conditional boundary, instead of equal to, I made it not equal to, and that mutation was killed. Great. because we know we had a test to test explicitly for null values. So we would expect this mutation to be killed. It also said that where it says less than 2, it changed that condition, conditional. Instead of less than 2, the opposite of it is greater than or equal to. And it basically what it's saying is when it changed the less than to greater than and equal to, the mutation was killed. Yes, we've got enough positive and negative tests. But what does this really mean? Conditional boundary. So what the conditional boundary is 2, right? So if you think of it, what the conditional boundary is if your conditional boundary is less than, if your condition is less than 2, the condition boundary of that is exactly equal to 2, right? So it is saying that when I change this boundary to some random number, maybe it made it 0, maybe it made it 1, 3, something, it changed it to something else other than 2, our test did not catch it. No test caught it. Because we have not explicitly tested the boundary. The boundary is word length equal to 2. The boundary of less than is equal to. So word length equal to 2, we have not tested that. We need to write a test for that. So let's try to write a test explicitly for that boundary of less than 2, which is equal to 2. Let me show you how we would do that.
Hi, Sualeh, we have a couple of minutes left.
Yeah, I'm almost done. So let's take a look at this. And I have written some additional conditions where I have written a test for 2-letter words, one positive and one negative. The words are oo and ah. Oo is a palindrome, ah is not a palindrome. Both of them are exactly 2 letters. Let's run the test again and see if we have solved this problem of the boundary condition. And it says, yep, all the 9 mutations are killed. Let's refresh the report and see what happens, right? And we have solved that problem. So what this really goes to show us is we can have 100% test coverage, but still our code may not be completely well covered to account for any possible changes in the future. And we need, maybe we can consider things like mutation testing to help us write better tests and additional tests. So that's quick introduction to mutation testing. It is compute heavy, so use it with care. I would not advise that you use it on very large systems. Use it on a smaller scale. Maybe think of using it infrequently because it comes with a cost, but it can be a very useful technique to to make sure that you've got great regression tests. So thank you, and I'm open to any questions that you might have.
Thanks for the insight. There is one question which I'll just bring up.
Yeah. So can we say that for every applied mutation, we will have equal TC? Sorry, what is TC? Test case or something else? Or Sumit, if you want to come on the voice call, we can talk about it.
Okay, sure. Yeah, I was about to say test case. Yeah.
No, not necessary. You saw that with our existing test cases, 8 out of 9 mutations were killed.
Okay, so yeah, okay, I got it right.
Yeah.
Thank you.
Sure. Anybody else? So mutation testing frameworks are available for all major languages today. So this is a good thing. No matter what language you're using, whether using Java, Python, whatever, you'll be able to find a mutation testing framework that will be able to help you.
Yeah. Thanks, Suresh. It was a really wonderful session.
Yeah.
And I really want to thank you for this.